this lecture, we will discuss about the networks, and an optimization problem is associated with these networks. That is, finding a maximum flow from an origin to a destination. So we will first define what is meant by a flow of a network. So we will first define what is meant by a flow of a network. And then the second thing that we will do is we will find cut of a network. And here this parameter will be a maximum parameter, and this one would be a minimum parameter. Cut would be calculated in terms of minimality. And the third part is we will prove the max flow min cut theorem. And if you prove this, then we can say that maximum flow is equal to min cut. So you have two problems: finding out the maximum flow, and its dual problem will be finding out the minimum cut. Whichever is convenient, you can use it and find the flow of a network. And of course, in the subsequent lectures, we would define an improved or a beautiful algorithm called as Ford-Fulkerson algorithm, which helps you to find the maximum flow of a given network. So these are the things that we will be covering in this particular unit. So we will first define what is a network, and then we will define flow, then cut, and we will prove the maximum flow and min cut theorem in this lecture. And in the subsequent lecture, we will illustrate the Ford-Fulkerson algorithm using some examples. So these are the things that is planned for these subsequent lectures. Now, I will first define what is a network, and then we will discuss about the various terminologies that we use here. Okay. So now the first thing is a network, capital N, okay, is a directed graph. You know what is a directed graph? A graph with the edges are being directed, which has direction. A directed graph is a network V, A with two distinguished non-empty disjoint subsets. Two non-empty disjoint subsets. Okay. X and Y of the vertex set. X and Y of the vertex set. Capital V and a non-negative and a non-negative integer valued function integer valued function C defined on the edge set or what is also called as the arcs, capital E. Okay. The vertices X are called sources of a network, and the vertices Y are called sink of a network, Okay. The vertices in V minus of X union Y are called intermediary vertices. Okay, intermediate vertices of a network. So you can have more than one sink or destination or terminus, whatever we call it. And similarly, you can have more than one source. But what we will be doing is, we will be concentrating on a single source to single sink model. Okay. So the vertex set is partitioned into three subsets, namely the source and sink. Okay. And the vertices apart from the source and sink are called as the intermediate vertices. Okay. So now we have defined a function C on the edge set. Okay. The function C is called as the function C is called the capacity function of the network, is called as the capacity function of the network, capital N. You can denote the network, we denote the network with the letter N. Okay. So in this case, the function C defined on its set is called as the capacity function, and you will have a value C of A designated to every arc, and that is called as the capacity function. Okay. So in this case, all these can be illustrated using this example. Okay. So now what you do is, we take, okay, a network like this, very simple network. Okay, this will be your X, V1, V2, V3, V4, V5, V6, and this one will be Y. So now let me give you the capacity: 4, 3, 8, 6, 2, 5. Okay. This one has 3, this one has 4. Okay. I'll take this as 5. Okay, 5. Now what I have to do is, this is an undirected graph. I have to assign a direction like this. So now you have a direction like this, you can see that there is a direction. Okay, you have a direction. You have a graph like this. This represents a network. Okay, you can see that this represents a network. And now, if you look at this X, which contains only one vertex, this is called as the source. And I have capital Y, only one sink. Okay, you can see that. Suppose if I have a quantity of goods at X, I want to transport it to Y. Okay, I want to transport it to Y through the path that is given here. Either I can take V1, V3, V6 and reach Y, or start from X, go to V2, V4, V5 and Y. Okay, so I got more than one path. Now what I can do is, what I have to do is, I have to find how to transport the goods available in X to the terminus Y. So you can also think of a water network. You have a source X, you have to distribute it to the sink Y, and you should push the water to a maximum extent. So those type of things can be thought of as a network, and finding out the maximal flow would be a solution to those type of problems. So here X is a source, Y is the sink, and I represent the intermediary vertices as V of X comma Y, V minus of X comma Y, which would be V1, V2, which would be the set V1, V2, V3, V4, V5 and V6. So intermediate vertices are 6. Okay. So now what I have done is I have defined a function C from the edge set or the arcs to the set of all integers, positive integers. Okay. So this is called as the capacity function. Okay, and now if you look at this, capacity of the edge X V1 is 3. Okay, that is I can push only 3 units from X to V1, that is the meaning here. And similarly, C of X V2 is 4. That is I can push 4 units from X to V2. And similarly, if you look at this, C of V2, V4, that is going to be 5. Capacity of the edge or an arc V2, V4 is 5. So, we have defined 3 terminologies here. Number 1, source, sink and the intermediary vertices. And the next one is the capacity. Next one would be the capacity of the arc. And now, apart from these definitions, terminologies, we require some more, which I will illustrate here. Let capital N be a network. Let capital N be a network. Let F be a function from A to R. A is the set of all arcs. Okay. It's a real valued function. Be a real valued function defined on edge set, or what you also call it as an arc for undirected graph. Okay, A of n. Okay, if I take a subset of A. Okay, then what I do is I find the sum of the weights f of A in K, okay, is denoted by, how do you denote it? It denoted by f of K, f of K. So I denote this with f of K. Okay, so now what we do is I take a subset, and if I add the weights of the subsets of the edges or the edges in the subset, then that is denoted by f of K. Suppose if I have more than one set, then f of S1 would be sum of the weights of the edges, This is different from the capacity. Okay, capacity is fixed. But whereas here I define a function, and later what I will do is I will call this as the flow. And what we have to ensure is that the flow is smooth, so that you get a maximum flow. And for that we define this function f. Okay, so now we require some more additional terminologies which I will define here. Let S be a subset of the vertex set. Let S be a subset of the vertex set V of n, of the vertex set capital V of n. Okay, this then a complement of S, which is denoted by S bar, okay, denotes the set V minus S. Okay, I use S bar as the complement of S. Okay, and what I will do is I will define, or I will indicate S comma S bar to denote the set of all arcs of n, arcs of capital N, okay, which have their tail, in S, and head in S bar. Okay, tail in S and head in S complement. Okay, similarly when I denote it with the S bar comma S, which means that the tail is in S bar and head is in S. Okay, so in this case such type of arcs or edges are denoted by S comma S bar. Okay, and now what you do here is we also define like this, or we can also write like this. We write f plus of S, okay, as summation f of E belongs to S comma S bar. Okay, so in this case what we do is you take the edge or an arc which is in S comma S bar, and if you just count the sum of the weights on the arcs, then that is denoted by f plus. And similarly I also define another term, okay, what is called as f minus of S, and this would again be the same quantity f of E, but whereas here E should be in S bar comma S. you know what is, in fact I'll write like this more better. E is in S bar comma S. Okay, so in this case you know what is S comma S bar. That is the set of all edges whose tail is in S and head is in S bar. Similarly, S bar comma S is nothing but the set of all arcs whose tail is in S bar and head is in S, because you are partitioning the vertex edge. You are partitioning the vertex edge into two subsets, S and complement of S. Okay, so once when you do it, it will be easier for us to define what is meant by a flow and how to find the maximum flow of a given network. So in this case, what we will do is, I will illustrate. Okay, I will illustrate this using. I will illustrate this using an example here. Okay, let me move to the next slide. Okay, I have like this. So let me take the same network. Okay, it's somewhat similar. X, V1, V2, V3, V4, Y, V5, V6, V7, V8. Okay, I have like this. So your origin X is small x, capital Y is small y, and the intermediary vertices are V1, V2, so on, V8. Okay, here I am not giving you the capacity. Suppose if I take X is equal to S is equal to X comma V1 comma V2 V5 V6 V3 V3. Then my complement of S would be the remaining vertices. V1, V2 is there. So I'll have V3, V4, V5, V6 is here, V7, V8 and Y. Okay. So now what will be S comma S bar? S comma S bar will be the set of all arcs whose tail is in S and S and its head will be in S bar. Okay. So now I have V2, V7. Okay, V2, V7. This will be one arc which will lie in S comma S bar. And the next one would be V6, V6, V3. Okay, because V3 is in one component and V6 is in another component. So I have V6, V3. Okay, so now I have two edges, two arcs. Okay, two arcs. Now I'll have like this. The direction is imparted in the case of the directed graphs. So here you have S comma S bar as the set of edges whose tail is in S and head is in S bar. And similarly here S bar comma S is empty. You don't have any edge or an arc whose tail is in S bar and S and its head is in S. So this is the set. In fact, what I will do is I will call this as a cut later. When I remove these two edges, then the component S and S bar, gets disconnected. The graph gets disconnected, and therefore it will be called as a cut. It will be called as a cut. So in this case, these you have to remember these terminologies. Okay. So now what I will do is I will define the important one, what we call it as the flow. Okay. An integer, let me write like this, an integer valued function, okay, f defined on a, f defined on the set capital A is said to be a flow. Okay, this is important, as I told you, because this has to be calculated at a later stage. A flow in capital N if, okay, said to be a flow in capital N if the following conditions are satisfied. Okay, if 0 less than or equal to f of a less than or equal to c of a for all c in for all a in capital A. So your flow should be less than or equal to the capacity of the edge. Okay, and the second one, this is again important, f plus of v is equal to f minus of v for all intermediary vertices. For all intermediate vertices. That is, incoming value should be outgoing value for all the intermediary vertices. And if these two conditions are satisfied, then the flow, the function that you define, is called as the flow here. Okay, so now the condition 1 that is stipulated here, condition 1 is called the capacity constraint. Okay, is called the capacity constraint. And condition 2 is called the conservative condition. Condition 2 is called the conservative condition. So in this case, a flow is a function. Okay, it's just a function which satisfies these two conditions: 0 less than or equal to f of a less than or equal to c of a, namely the capacity, and incoming value should be equal to outgoing value for all the intermediary vertices. And the first condition is called as the capacity constraint, and the second condition is called as the conservative conditions. Now what we will do is we will illustrate this using an example. Okay, I have like this x, it goes to V2, and here I take flow. I take the capacity as, okay, I take the capacity as 4 for the edge x V2, and now for this edge, okay, V2 V4, okay, V2 V4, I will have like this. The capacity would be, the capacity would be 5. And for this V5, call this as V5, the capacity would be 2. Okay, similarly here V1 capacity is 3, and for V3 the capacity is 8. I'll take this would be V6, capacity is 5, and here I have Y with capacity 3 and V5, V4 with capacity 4. Okay, so now what I do is, if I want to ensure that I have a flow of a network, okay, so now what I do is, I will push 2 units. Okay, for my convenience, what I have done here, I have pushed this 2. What is this 2? 2 is nothing but the smallest value here. And if you look at this, every arc, okay, in every arc, the function f, which is 2 defined on the edge set, is always less than or equal to the capacity which is given here. So the units of goods that I push is given within parentheses, which would represent a flow. And if I take any intermediary vertices, okay, the incoming value is always equal to the outgoing value. Here I have taken a constant. I can also vary from one vertex to the other. Okay, so for our understanding, what I have done is I have taken an universal value 2, which means that the incoming flow is incoming value is 2, and similarly the outgoing value is also 2, so that I get a flow which is very smooth. And this flow I have designated because the minimum capacity among all the edges is 2. Okay, it is not necessary that I have to take 2 always minimum value, but here what I have done is to illustrate this in an example. This example I have taken 2. So you can also take any value, but you have to see to that the 2 conditions are satisfied, namely the capacity constraints, that is the flow should always be less than or equal to the capacity of the arc, and the second thing is that for any intermediary vertices, the incoming value should always be equal to the outgoing value. Okay, and in the case of the source, incoming value would be 0, and in the case of the sink, the outgoing value would be 0. So that you have to keep in mind. Okay, so now let me define the next part. Okay, what is it? Yes, a little bit of calculations, what you call it as the value of the network. Okay, so now I will define what is the value of a network. Okay, so for this, let me define like this. Let F be a flow. Okay, so now what I do is let F be a flow in a network, V, A, C. Okay, this would represent the capacity. Okay, so I have introduced a triple. Okay, it's not necessary. You can skip it when C is understood properly. Okay, then for every subset, S in V, contained in V, okay, the value f plus s minus f minus of s is called the resultant outflow, is called the resultant flow out of S, and f minus of s minus f plus of s, okay, the resultant flow into S, resultant flow into S relative to C, relative to the capacity C, relative to the capacity C, or relative to, in fact, you write it as F, because this is relative to this function. Function is a flow depends. You can change, keep on changing the flow. So relative to F. Okay. If S contains, let me write like this. This is easily understood. If S contains only the intermediary vertices, okay, if S contains only intermediary vertices, then, or intermediate vertices, then what would be the value of f plus of s minus f minus of s? Okay, any guess? Yeah, it is right, because it will be 0, because f plus of v will be f minus of v for every v in the intermediary vertices I. Okay, so in this case you have like this. So f plus, okay, f plus s minus f minus s is 0 if you have only the intermediary vertices. So now I have defined many parameters. Okay, so these are all the parameters which we are going to use to find the flow. But you have to keep note of this. Okay, these terminologies have a minute difference. Okay, so now what you have here is, okay, if you think of this f plus, okay, let me write like this, f plus of s need not be equal to, okay, need not be equal to summation f plus of v in s. Okay, that you have to keep in mind. Okay, so now what we do here is, once defining what is meant by flow, you are now concentrating on finding out the sum of the values, flow, what you call it as the value of the flow. Okay, so in this case, if you look at this juncture, okay, for every, let me write like this, for every s contained in v, okay, you have f plus of s minus f minus of s. Okay, this would be equal to sum of f plus of v, okay, where v belongs to s minus sum of f minus of v in s bar, okay, or I will write like this, v in s, okay. So you can see that even though they are not equal, you define f plus of s minus f minus of s as this, okay, and for all the intermediary vertices this would be 0, okay. So now what we have here is this f plus of x minus f minus of x plus f plus of intermediary vertices minus f minus of the intermediary vertices plus f plus of y minus f minus of y. This has to be 0 because this has to be 0 because of the conservative condition, and because you know that the intermediary vertices are 0, so you have f plus of x minus f minus of x, this would be f plus of y minus this would be f minus of y minus f plus of y, and this ensures that the flow, okay, the flow in the from the origin is equal to the value received at the sink or the terminus, okay. So this is important here because the value that has been pushed from the origin is going to be received at the sink, okay. And as I told you, you can also have more than one origin and one destination, and their network will be like this, okay. I can also have like this, okay. I will take another one. Okay, here I will have x1, x2. Here I will have y1, y2, y3. Okay, here I will have v1, v2, v3, v4, v5, v6, v7, v8, v9, v10, v11. Okay, this would be a network. Okay, I can also give the capacities. Okay, capacities, all those things. Here, if you look at this, you have S. Okay, what is this S source? Or I have been representing it with X. X will be X1, X2, and Y would be Y1, Y2, Y3. Okay, you can see that. And what is I? I is the intermediary vertices, which are V1, V2, so on up to V11. Okay, so these are intermediary vertices. So this is an example. This is an example of more than one. Okay, you are like this. More than one. Okay, more than one sink and source. Okay, you can also have like this, but what we will be doing is we will be concentrating only on a single source and a single sink. Okay, single source and a single sink. Okay, and now I will introduce another terminology, what you call it as the saturation of a vertex. Okay, what is meant by saturation of a vertex? Okay, or saturation of a arc. Okay, of an arc. Okay, so now what is this? Given a flow. Okay, now what I do is I take a flow F in a network, capital N. Okay, an edge is said to be, an edge E is said to be saturated, if f of E is equal to C of E. What is the F? That is the flow that you consider, and the C is the capacity. C is said to be the capacity of the edge. Okay, the edge E is said to be unsaturated. Okay, now you have like this, unsaturated if f of E is less than, okay, you are like this, if f of E is less than C of E. Okay, so you have like this, if f of E is strictly less than C of E. That is, still some more flow can be done. Then that is called as the unsaturated edge. Okay, and the main thing is a maximum flow. Okay, a maximum flow in a network N, in a network capital N is a flow, okay, is a flow that achieves, okay, that achieves the largest possible values, that achieves the largest possible value. Okay, that achieves the largest possible value. So the maximum flow of a network will be the flow which is going to be the maximum, okay, and in the case of the maximum flow, okay, in the case of the maximum flow, what we have is the value of say for example, if you have like this, I'll write like this, more appropriate. If f dash is any flow, then f is maximum flow if value of f dash is less than or equal to value of f. Okay, this has to be true for any flow f dash of f, for any flow f dash of f. Okay, so this would be the flow. So now let me just give you in brief what are all the things that we have seen till now. Okay, you had defined what is a network. Okay, then you had defined what is meant by a capacity of an arc. Okay, then you had defined what is meant by a flow of a network, and then after that we had defined what is value of a network, that is sum of all the flows. And after the values, you had defined what is meant by a maximum flow of a network. So these are the things that we have seen till now. Now what we will do is we will move to the other part, what you call it as the cut. Okay, what you call it as the cut of a network, or a capacity of a cut. Capacity of a cut. So that we will be defining now. Okay, what is capacity of a cut? Okay, now let me write like this. Let capital N be a network. Let capital N be a network with a single source, and a single sink, Okay, a single source and a single sink Y, and single source I'll denote it as X. Okay, let S be a subset. Now what I'll do is let S be a subset of the vertex set, of the vertex set will be the subset of the vertex set S. S be the subset of the vertex set of the network N. Okay, such that X belongs to S and Y belongs to S bar. Y belongs to S, complement of S. Okay, I will have like this, Y belongs to S bar. Okay, then S comma S bar. Okay, I have defined as the set of all edges whose head is in S bar and tail is in S. Okay, then I define S comma S bar as the set of edges. Okay, as the set of edges, with the tail in S, and head is in S bar. and head is in complement of S. Okay, and you have to be specific that S bar is V minus S bar would be V minus S. Okay, this is called as a cut in N. It is called as the cut in N. Okay, and here the capacity, the capacity of cut S comma S bar is the sum of the capacity, is the sum of the capacity, capacity of edges in S comma S bar. Okay, so now what I do is I take all the edges which are in S comma S bar, then add all its capacity. That would be the capacity of the cut. Okay, so we have defined an additional parameter, what you call it as the cut. Okay, and now what we will be doing is, we will be proving these results. This I will do it. In the next lecture. But now what I will do is I will just give you what are all the results that we are to prove in the next lecture. The first theorem that we will be proving is that the value of any flow, in a network, capital N is less than or equal to the capacity of any cut, in a network. So this will be the first result that we will be proving. The second result that we will be proving here is, the second result, which is also given as a theorem here. Let F be a flow. And capital K be any cut or be a cut in a network N. Such that value of F is equal to capacity of K. Then you prove that F is maximum flow. F would be the maximum flow and K is minimum cut. So this would be the second result that we will be proving. And of course, you have the final theorem, what do you call it as the max flow min cut theorem. It is an important result here, what you call it as the max flow min cut theorem. Max flow Minkach theorem. Which is like this: in any network, okay, the value of maximum flow okay, is equal to capacity of a minimum cut. Is the capacity of a minimum cut. Okay, so in the subsequent lecture, what we will do is we will prove these results. We will prove these three results, and using these results, we will find the maximum flow of a given network using the Ford-Fulkerson algorithm. Okay, I will stop with this, and if you have any doubts, you can just mail to Venkatakrish2 at max.sastra.edu. I'll be happy to answer all your queries. Thank you.